Yeah, anyway, this is a small exercise that me and Alex did um, with just a bunch of hours that we set up as a consultancy with NeSI. And our um, intent was to try to figure out if we can classify images. I don't know, we know that people do classifying in different kind of images using convoluted neural network. And so we had the idea of what we, if we treat spectrogram of signals as images and see if we can classify them. And the reason is that at NIWA we're developing a strategy for using passive sonar technology to monitor underwater environments. So there's so many sources that we have to deal with and classify, and these are human-generated sound from shipping, constructions. There's sounds in the ecosystem that comes from animals that live in the ecosystem, fishes, invertebrates, marine mammals. There's geophysical sources like earthquakes and landslides. And obviously it's very important to measure and monitor these kind of sound sources if you want to understand ecosystems. And we have a program in the raw sea to do that. So there's a lot of, we're acquiring a lot of data. In particular, there was a project in Cook Strait that's now ended, but we still have a lot of data to analyze. And there's about 12 terabytes of data, maybe more. And it's 1 year of recording at 7 different stations. So it's kind of like 7 years. We have the raw sea ramp in which we are acoustically monitoring like 3 locations in the raw sea. One is Iselin Bank, one is near Scott Sea Mountain, and the other one is near the Pacific Antarctic Ridge. And so far we have 1 year of recording that was recovered in 2019 for about 3 terabytes of data. But we're planning to keep the moorings down until 2023, so it's going to be a very long-term data. So in terms of sound signal that apply to marine mammal research, the complexity is that we're dealing with a lot of taxa, and there's all these taxa that they evolved like different kind of communication system and also like sensory system to sense the environments using sound. And so we're pretty much dealing with a lot of signals that span over large frequency ranges from a few hertz to hundreds of kilohertz. They may include frequency and amplitude modulations. And also the duration of the signals varies because the collocation signals are really short. We're talking about a few microsecond signals down to tens of seconds for large baleen whale calls. Some example just to give you an idea what we're talking about. If there's an earthquake, that's the door.
Well, no.
That wasn't.
That's holding the cover to it before you run through the door.
So, but anyway, so just to give you a brief example, these are spectrographic representation of sounds of different marine mammals. In this case, these are fin whale calls, and I'm not sure if everybody is familiar with a spectrogram, but you're pretty much transforming the time domain of the signals into a representation that extrapolate the energy content at different frequencies. So you have frequency on the y-axis as a function of time on the x-axis, and these red blobs that you see, these are the calls from the fin whale, and they're in the order of the 20 hertz. So just to give a perspective, in seawater, that's a wavelength of 75 meters. And these are social sounds, for example. Other type of social sounds are from, for example, this is a blue whale. Sorry, I don't know why the thing's not working, but so these are Z call from a blue whale. Same kind of order of magnitude of the frequencies. We're talking about 25, 20 hertz. And it's this little Z things that we see in the spectrogram. We have other type of social sound from dolphins that are very long signals that sounds like whistles, and they're frequency modulated. They're the one in the little rectangle in the spectrogram. You can see they're all these squirrely kind of sounds, many seconds long. We also have echolocation, and there's two type of echolocation signals in it, actually three. One is kind of like, it's called broadband echolocation signals. Most of the dolphins, killer whales, sperm whales use this kind of sounds. And is those little vertical lines that you see, those are really short, impulsive signals that animals use for sensing the environment. I don't know what's going on here. Need to rejoin the meeting.
Just press on the orange.
Yeah, this one.
Yeah.
Yeah, but we're not seeing the
Just
share.
go back to
I have to share the screen.
share the screen.
There we go. If you close this. Oh. Sorry.
Is it this? Okay, I think
Okay.
I'll just go back. I'm used to the slideshow. Might have to just go quickly.
Let's go back. That's fine. Yeah. Sorry, we had to join our own meeting to share the screen, and it was a little bit problematic. But so the broadband echolocation sounds, super short pulsive sound. They span over a wide range of frequency from 10 kilohertz up to 40, 50. And there's also like small dolphins and porpoises that they use like narrowband high frequency echolocation signals that they are like in the range of 130 kilohertz for peak frequency, but their broadband their frequency range is shorter. So this is just to give you an idea of at least the variability that you have just within cetaceans of the kind of sound that you look for in the data sets. And you know, you can do this doing one task at each time using normal signal processing, detection, classification algorithm. But we need to develop a way that we can do it like consistently and cost effectively. And these are another kind of sounds that we've been working with Alex. And these are frequency modulated echolocation signals that are produced by beaked whales. And the beaked whales are the only taxa in the cetacean that they frequency modulate their echolocation signals. So this is like a snapshot spectrogram of 1.4 milliseconds of time series data. And looking at the Cook Strait data, we identify like these three types of echolocation signals that we believe, we know that one belongs to Cuvier's beaked whales. The other two, we don't know what kind of species makes it, but we presume that they're from two different other species. And so this is the same old big data problem. We're collecting so many data that there's so much information in the data, and there's no money to actually look at everything. We had the challenge to cost effectively classifying many types of signals in the data. and as I was saying at the beginning, NeSI had this little project that you can use as a consultancy, so that you can try to use their technology to analyze your data. And me and Alex, we team up together, and he developed pretty much patchwork available software in artificial intelligence that is commonly available, and pack it up into a Python script that would try to train a convoluted neural network to classify those 3 big whale sounds that I show you. And so from now on, I'll leave you guys with Alex, that is going to explain the model that he created. Alex, who are you? You are a physicist. You've been at NeSI for many years.
No, I actually just joined NIWA and working for NeSI. It was maybe 3.5 years ago. So I'm actually fairly senior in that respect. In our group, I think we have many more people who have actually joined since then. So originally a physicist, but like many physicists, we tend to sort of drift and into the unknown. Yes, that's it. Thanks, Giacomo. I realized actually today that I knew very little about Giacomo. So although you introduced me, I just realized that just reading a little bit what you did and so forth. So just to say that Giacomo, apart from being a very good ping pong player and participating in the tournament, you did your studies at University of Hawaii.
Yes.
Oceanography.
Yeah.
And I've been working with NOAA and working.
I did some project with NOAA in the past.
Yeah. Right, that's great. Well, so I, it was not a huge amount of work, and in some sense, maybe one of the main messages I want to convey here is you don't have to be an expert in using machine learning. I mean, certainly, I don't consider myself as an expert, and this is not an area where I naturally fit in. I'm like partial differential equations and these kinds of things, and more recently interpolation. But yeah, that's. But so maybe one of the messages that it's not actually that difficult. So with a little bit of tools and a little bit of experience, I think a lot of you will be able to do something like that. But machine learning is a bit like a dance, and there are a couple of steps, and the steps have to be learned. But the first one is you get a feel for the data. Actually, forgot to do that. We did that.
I had already.
Yeah, Giacomo did that. Then you choose a model depending on the type of data, the kind of problems that you have to solve, and you have to train the model. You have to test the model. You don't have to do a live demo, but I'm going to do that. And maybe also going to talk about performance, because as we started talking about 12 terabytes of data, then at that point, although this in particular fit, that particular problem fits very nicely on a laptop. I mean, it's just something that you want to consider, and we have platforms that will do that quite efficiently. And finally, some lessons learned, but this is really a two-way communication. So if you have some comments, suggestions, and so forth, I'd be very happy to learn from you as well. So the first thing is I'm trying to sort of slip into the shoes of a scientist who has to do some machine learning and so forth. So the first message also is if you're a little familiar with bash commands, that's going to help you a long way. So Unix and so forth. So this is just an example of a command. So we have a directory called train_data2. We have inside that directory, we have 3 categories of data. So these are the labeled data. We're doing supervised learning here. So we're starting with data that we know already. That's for the training. Obviously, ultimately, once the model is trained, then we can supply data where we ask ourselves, what kind of signal, what kind of sound was that, right? And so each directory here, folder, so 3 of them, they have been already classified by a human, and so they've been labeled. But the first thing that you want to find out is, how many samples and how are the samples distributed. So this is a little command. So you have you do a ls list, date, strain data, whatever the name of the folder. Star means, any of the 3 folders underneath. And then we started with PNG files. And then you pipe that to WC, word count, -W, you just counting the words, and you get some numbers. So very, very quickly, so you get 265 samples for one, 306 for the other one, and only 48 for Cuvier. A bit disappointed here, Giacomo. But that's reality. That's what happens, and so essentially you only have 4% of the data for Cuvier. So we expect here to have a little problem. So this is another nice little command, which, by the way, I sort of figured these things out afterwards when I was asked to actually lead a seminar to do that. But I'm happy to share that. And so we're creating a little loop over these 3 categories: 53 kilohertz, 93 kilohertz, on some unknown wave type. We're not quite sure what it is. Then we have Cuvier. And then, but perhaps you want to see, how different the data are. And so you don't want to really see the 603, whatever category it was, because that's really painful. So this little command here will extract, 20 pictures randomly. And there's a command called shof on Linux or gshof on Mac OS X. But you sort of pipe that, you convert that into a little movie, and then what you get is, what's actually running here. So the first thing is when I look at that, so on the left-hand side we have the 53 kilohertz, and that's I can see a pattern here. Okay. First, the first thing to say is that all the axes are the same: time, frequency. Nothing changes, right? So that's the first thing. The second thing is that, as a human, I think I'd be okay recognizing the left one from the 2 other ones, but the 2 other ones, sometimes they overlap a little bit. The middle one, 39 kilohertz, you can see that kind of sound where it sort of goes up in frequency over time. But it's still, and the Cuvier might be a little bit noisy, but there's quite a bit of variation regarding the Cuvier one. So I'd sometimes would be difficult for me, and sometimes it's also difficult to differentiate the 39 kilohertz from the 53. So that, okay, now that we have a bit of sort of a feel for the data, I think the next step is to choose a model, and the rule is that if you're starting with images or fields, they could be 2D or 3D fields, you probably want to look at using a convolutional neural network. And here I'm just going rapidly through the steps of what it means. So I copied these pictures from YouTube. They're not of the greatest quality, but I really like them because they very simply sort of tell that story of how we can detect possibly an X or differentiate an X from an O, a handwritten X from a handwritten O, let's say, on the left-hand side. And bear in mind that all these X's at the top or the O's at the bottom, we as humans, we obviously recognize them immediately. Yes, it's an X. But now the difficulty is, or the challenge is to tell a machine to recognize. And so they're never going to be perfect X's, they're never going to be perfect O's, and still the machine has to be, has to come up with a number that says, I'm confident this is an X. So the way it works is that we're going to look for little patterns, and the patterns are the things that are on the top right. So if I use, I'm just going to focus on the X for simplicity, but if I want to sort of identify, locate an X, then
then I can think of 3 types of patterns that should be present in the picture. I don't know exactly where, and they could be at different places, but an oblique line going from the top left to the right bottom, a sort of a cross, and the for the middle, and then the other way, sort of bottom left to top right, kind of diagonal going across. And I can see those patterns in my X, even if the X is distorted. So this is actually called a filter. So the reason why I'm talking about that is that the software that I assembled for Giacomo allows you to choose the number of filters. So here we think that 3 filters would be enough. But in general, if you want to recognize a car, or differentiate between a car and a bicycle and these kind of things, you might actually need vastly more filters. And by the way, just feel free to just ask questions along. So far, so good? Yeah?
Yeah.
Oh, yeah.
So just from before, like, what are the 39, 56, and Q? Is that different call from the same species or different
No,
species?
those are the 3 categories that we're trying to classify.
Yeah, but what actually are they? Are they from different
So the
species?
cougar is from one species, the
Yeah.
33 and 39, the 2 species probably.
Okay.
different
Oh, so you don't
species,
know
but
what they
we
are.
don't know what species.
Okay.
We don't know. Yeah. Okay. So thanks. So the other thing is that the machine, machine needs to come up with a scheme by which it can sort of see how close 2 x's are. So on the left we have the perfect x, on the right we have that mangled, distorted x, and as humans, I mean, we do see that x pattern, but how does the machine see that? So we have to come up with a scoring system. And a simple way is to let's associate every black little pixel that makes up the picture with a -1, every white one with a +1, and then let's apply a dot product between these 2 pictures, meaning we just flatten all these pixels into a 1D array, and we do multiplication and adding all the terms. So what you will see is that every time the pixels match, you're going to have a 1, right? If you have a -1 pixel matching a -1, you're going to have a 1. If you have a +1 matching a +1, white, then you're going to have a 1. However, if there's a mismatch, then it's going to give you a -1, right? So that's going to decrease the score. And for this particular picture, which has a resolution of 10 by 10, then the maximum score would be 100, a perfect match. Everything is glorious, or -100 is completely wrong. Right? But it gives a little bit of a gradation, and that's how the system works. So that was it, in terms of introduction to convolution networks. Neural networks. I think we're sort of ready for attacking the problem, and a couple of steps. We want to randomly select images and feed them into our training. That's important because the gradient descent is going to adjust some little weights in the neural network. I didn't describe what those weights are, but there's some parameters that are stored inside the neural network, need a little bit of adjustment, and the final result, of course, is going to depend on which order you're actually feeding the data in. It shouldn't in practice, but in reality it does. So you want a bit of a randomness and shuffling going around. For this particular case, but that varies, but for this particular case, the red, green, and blue channels of the picture are not relevant. We're only interested in the in amplitude, the intensity. So basically, we want to convert those red, green, and blue into numbers. So we combine it. Yes.
Yeah. So I was going to ask that question. So you're using an image processing process, which is dependent on color, but those colors are artificially derived from amplitude.
Yeah.
So in this process, you're going back to amplitude rather than using color.
Exactly.
Okay. So that makes it less ambiguous based on the color map that you choose, which is I imagine the right thing to do.
Yeah, that's right. So I guess so. Thanks for the question. So because we started with pictures that actually use a color map that was cold to hot, using MATLAB, whatever.
That, though, we need to specify is relative amplitude.
Yep.
Yeah.
It's not the absolute
Yeah.
amplitude of the received sound.
Yeah. So the really important thing is just the consistency here. We eventually, just a color will map into an amplitude. We don't even care whether it's the right amplitude.
No.
When we do the classification, we don't really care.
It doesn't have to be calibrated. It's relative to the peak.
Yeah, but we're going to get a number, and that number is going to be very systematic to that particular color, and neighboring colors are going to have neighboring numbers, and that's it. That's a good point. The other thing is that we're going to interpolate the data to fixed size, so we're going to do a little bit more image processing. 100 by 100 in that particular case works pretty well. That's just because when we feed in some pictures, we sometimes they might be over a longer time span or something like that. But the pictures will be assumed to be consistent, so the scale and everything. But the number of pixels can actually
mean the time and frequencies.
Yeah, exactly. The scales of the pixels. And then we assembled the convolution neural network, which we talked about. The last layer, because we're doing a classification and we have three categories, so we're going to have three neurons that just take the input from all the key layers, and then what they spit out are probabilities for each of these three categories in such a way that the sum makes up for one. And so the neural network not only will give you what it thinks is the right classification, but actually what it's going to give you is a probability for each, and then it's sort of up to you to decide what you do. If it's 95% confident, you say, okay, but if it's 50, 60, then big question mark. And so the user is going to have to choose the number of convolution layers, which essentially handle the multi-resolution aspect of the data processing. So just imagine that sometimes we take a magnifying glass, we're looking really very closely and we're seeing something, and then we're taking that telescope approach, we see something which is completely different. So each layer is going to have its own filters, adjust its own, look for special patterns. And then the number of epochs, and I'm using here a little bit terminology that I think is useful for people if they want to get into machine learning, is the number of times you go through the entire data set. So in principle, you shouldn't have to go, but because of the gradient descent, the stochasticity and randomness of how we feed the data, effectively you want to go through, and we can see that afterwards. Then finally, we test the accuracy. So far, so good? Right, so we're basically ready for a demo. Let me just.
One quick question.
Oh yeah.
You are saying about the unbalanced data set for one of the categories. Yeah. So do you do any kind of data augmentation or something to balance the data set, or?
Yeah, very good question, Arjun. So maybe that's what's going to answer your question is if I let me just make that a bit bigger. Hopefully people can see that. Let me know if I have to make it even bigger. But so basically I wrote some software, and we have it's a Python software here, but it's called the project's called Balena que Canta. But train is the script, and so there's a little helper command here. So I think that's going to answer essentially your question, Jeff. So you can specify, how many samples we're going to take from each categories. And here, because we're very limited with Cuvier, 38 samples and so forth, and we want to keep some samples for testing. So maybe 20. I try to just use 20 and just see how it goes. sounds very limited. But for the other ones, we can be a little bit more generous. But there's a risk that if we use too many of the 39 kilohertz or 53 kilohertz data, then they're going to just overwhelm, the training, and the machine is just going to say, well, QVA is so rare, I don't care. I mean, everything is going to be either 39 kilohertz or 53. So that's a danger. So you want to play a little bit around with that. And another possibility is to actually use more than 38 for QVA, and that would be the enhancement that you're referring to. I think in that case, the script will just duplicate and just choose again the same picture. But we could have a match, and we can run that case if you want.
Sorry, a quick follow-up question. Would it make sense to artificially add QVA pictures by using distortions that you would expect from the measurement, just to add a bit of variety? I mean, obviously you can't mimic the natural variation in sounds because it's something you would need to at best model if you can do it at all, but at least to get a bit of for distortions, measurement errors, overlay with other signals. So to mimic that.
It might make sense, but I think it would be technically better if we actually would analyze more data and actually have real sample to add to the training. But let's let Alex finish because
I mean, I think
it's not that bad.
That's a technique. I mean, what Wolfgang is referring to is sometimes if you know exactly what you're looking for. I mean, for instance, if you're looking for bicycle pictures, then you can take the bicycle and just move it a little around, translate, increase the size, and do all these kinds of things. I mean, that's definitely a way to enhance a given data set. I think the challenge here is that it's hard to sort of to really sort of categorize, to really describe the QVA sounds in such a way where we can artificially. It would be hard.
It would be.
So,
it would be hard.
Yeah. So I'm going to just run locally on that particular laptop. So the directory is that training data set that we just used. Suffix just PNG by default. That's fine. So the important parameter here is the epoch. So we can start with 10. So we would go 10 times through the entire data set. And now for filters. Okay. So any suggestions here? So we can give a number of numbers, and these would actually be the number of filters for the finest resolution, and then a coarser resolution and coarser resolution. Rajat.
So always good to start small.
Yeah.
See how it performs.
Yeah.
If it performs well, then we
How small do you want to go?
So 8 maybe. 8, 16, 32.
Okay, so 16. That's actually pretty big for this problem.
Oh, okay, so 8.
But we can run with that.
Sure.
No, I mean it's going to run nicely, but it's not. Okay, we can go down even further. We're going to print the model. We're going to we're going to select. And I apologize for the resonance here, but maybe we just start with those numbers here for the time being. Let's go.
Given that there's already a lot of variation in each of the 3 different types, what would happen if you told it to classify into 4 things, for example? Because then it might tell you that maybe there's a beat where that's actually at 52 as well as at 53, but you've already predetermined that there should only be 3. So would you just have to fight just have to run it and see if it turned out with like better fit, if it had 4 groups instead of 3?
Yeah, so I guess there are a couple of interesting questions, and one of them is okay, what happens if you have 4 categories? You know, the code would sort of work, but of course you need more data, more training, and you need to, this is all based on labeled data, so you need to have a set of
For the 4 categories.
for the 4 categories.
You can create a 4 category.
But then you already have to know it's there to be able to find it there.
But I think another question that, you know, maybe wasn't explicitly asked here, but what if you throw in a 4th category that the system has never seen, right? And so in principle, in that case, I think the system will likely be confused and provide probabilities that are sort of like, it's a bit closer to this one, but really I'm not very sure. Just like a human would in some sense. And I can't run that demo, but
no.
Well, we could download that picture of a bicycle or something.
As you put it in.
Yes, that's definitely a thing. But just to answer, you know, I think we have to clap our hands for Raja because he achieved a 0.1% accuracy with, and the testing, so it was really easy. And the testing went over the entire data set. So there was only 1 that was misclassified, even though we actually left a lot of data for testing that the model hadn't seen. So in that particular case, you can actually go down to something like you can go down to something like that. Just for
You may be going to talk about it as your next step, but then that's on scrutinised data, your 906 scrutinised images. Have you applied it to unscrutinised data with some verification by the, I presume, Giacomo?
Well, we're not, the next thing of the demo is going to fit the trained model on a known picture.
Okay, that's
and we'll see what the
But you're still clipping pictures. You're still clipping pictures. So I'm looking at, you know, passive mooring data where you've got how many terabytes of data, and presumably you want this to run on the data set.
Yeah,
and without having to go through another process of actually identifying and clipping specific pieces of sound.
Yeah, the thing is, I know of people that have been applying this kind of technology to time series data without producing a spectrogram. And the limiting factor is that the large number of data sets for training is not working. So here we just did an exercise of what if we use this in the frequency domain with an image. So going back to your idea, yeah, it would be way more straightforward to go and classify directly the time series, pressure time series of the signal. But maybe we'll come later. Right now, what I was thinking is that in the grand scheme, you can have like detection system, a detection algorithm that just extract a signal, say an echolocation signal. And you know that the echolocation signals, they all pretty much shorter than 100 milliseconds or microsecond or whatever it is. So you cut them all at the same, in the same frame, and you make a spectrogram of all of them, and you feed it to the system. And so the idea is like if you have a high frequency narrowband echolocation from an ecto dolphins, the picture will look, the blob will look way high in the frequency, not having a frequency modulation. It would be a beat will would have some sort of frequency modulation. Sperm will be in another place. But yeah, it would be good if we could cut the process of going into the frequency domain.
I mean, it's a really good point, and we're going to talk about it afterwards. But I have to say that images also have one advantage is that we humans are very good at sort of classifying images. And you know, you look at signals, and it's a time signals and so forth. It's just not going to carry as much information visually. You know, it's hard to even show. You don't have enough pixels to show the intricacy when you something that goes to 100 kilohertz, and I think the spectrogram approach has that advantage of unfolding, in this human readable way.
It does give us a way to actually have a fast check on the performance of the system or create a data set for training. Because we have to do that anyway, the spectrographic analysis is.
You don't have a choice with this. I mean, they are called convolutional neural networks. They are made to work on images. They're designed for computer
Yeah,
vision.
it would be definitely it would be the recurrent neural network.
Yeah.
We understand. Yeah, so you will not be able to use that particular neural network model, which is designed to work for images or data. That's a strong correlation between delivery.
It's the same way as, I mean, ideally you would feed the actual spectrogram data to the system, but you have to save them as picture file because that's what they're designed for. Like that whole library is about, like, you have to feed them like PNG images.
No.
Can you feed them like matrices, like in an NumPy format?
So that's what we do here. So basically we go from the
No,
pictures into
Yeah, but that's what I meant. You I mean, the data is not a red, green, blue data originally. It's just a value of amplitude. So why do you need to create pictures in red, green, blue if then you're going to recollapse them?
We wouldn't have to.
We wouldn't have to.
We wouldn't have to. Just that. But yeah, that step can be definitely removed. Anyway, so I ran again and with a 4x4, so 2 hidden layers and 4 filters only. Did even better. Sorry, better. But and we down to basically no mismatch.
Alex, can you go up and show us what the print model actually produced, the structure of the model?
Oh yeah, that's a good thing. So we have basically 2 convolution layers with max pooling. They essentially go together. But just to go, the details are not so important, but the input are 100 by 100 images, and then we have these 4 filters, and then because of the coarsening, at next level, because we had 4,4, so then we're looking at features on 50 by 50 images, if you want coarser images, and again we're applying 4.
So do you mean pixels or images? Is it?
Yeah.
Images or pixels?
Yeah, you can think of them as being pixels after the coarsening. So each level basically looks at different resolutions. So the finest resolution is 100 by 100 here. We have another layer that looks at 50 by 50, and we have four filters. There's the max pooling that finds what's the best. The best patterns and things like that, and then eventually we just flatten everything to a dense layer with 3 output, and the number of trainable parameters are 8,000 here. Yeah.
What activation function do you use?
The value, I think. Yeah. So there's always. I didn't go into the details. We can take a look into the code, but I think it's usually the value. So it's I'm gonna try and. Oh no, it's not in this file here. It's in. It's not. I didn't make it a parameter. Yeah, but that can be changed and maybe some. I think it's a build model. Yeah, so for people who just want to take a look at the code, I'd be happy to chat. Okay, any more questions? And then we essentially ready to wrap up. Let me see. Okay. So So we talked here about this is the topology of the neural network. We had 2 convolution layers, second one, output 3. So we just went through that. I guess another thing that I just wanted to mention is that although that ran really nicely on my laptop, and it will do that very nicely on your laptop as well, I'm sure. It's interesting to see, what when if there's any benefit in running on a supercomputer platforms, and for that I had to sort of change a little bit. Make the model more complex, so having 32, so four layers with 32 filters each, not really necessary in this particular case, but we imagine that maybe that's going to be necessary for the bigger data sets, or when we have more species, or want to discriminate between human and whales and dolphins or whatever. And of course, vastly more training sets so that everything runs much slower. And on that particular laptop, using the version of TensorFlow that I installed using Conda, it took about 280 seconds or so. If you were to move to Maui, Ansel, which is a platform that we have access to here at NIWA, then and if you follow the instructions given by Wolfgang on how to run efficiently on CPUs, then you would get already a pretty nice speed up. But now you can start to add more threads, right? And you can see that the execution time, the wall clock time, comes down to something that is, maybe 10 times, not 10 times, but 8 times faster. And if you run on my Huika GPU, then you get about 15x speed up. So, that's something that may actually help you for your next project, Giacomo or anybody else. So just keep in mind, nice to start on a laptop, but if you need a bit of more oomph or power, then we can help you with moving to our supercomputers. So lesson learned. So I was given TIFF files, and I just converted them to PNG, much more compact, much smaller. That really helped. I should emphasize that this was really a brute force approach. We didn't muck around with the data. We didn't. Let me just fix a little bit of the input. There was no time, but we just took the pictures we had. We had a question: why did we produce the pictures? We could have used the intensity files, right? Good question. This is just a starting point. So we just wanted to use the convolution neural network, something that is very mature, and I think performed beyond our expectation, even though we only had 38 QVA samples. There was a question about using perhaps the time series, in which case we would have to use the recurrent neural network topology, presumably. People have worked on it. Probably a solved problem, just we don't have any personal experience on it with it, so we can't really say to what extent it will work or whether it's better or not. There's always possibility to use dimensionality reduction on top of that, principal component analysis, anything like that. But the neural network will actually do that for you as well. So it's not really necessary. It might be beneficial, particularly if the data sets are huge. Overfitting is your enemy. So just as Rajav said, start slow, just go as coarse and as a small model as possible. I think it's going to be much more robust. And we, 4.4, for instance, were able to actually solve the problem very nicely. We used open source and free software. We didn't have to handle licensing issues and so forth. So everybody can install that on Linux and Windows and Mac OS X and run on our platforms. It helps to know a little bit of Bash, it helps to know a little bit of Python and Git. And all these skills, you can learn them at the Software Carpentry. There are some sessions every year people can attend, and you can do this.
So one thing that you didn't show the actual classification task.
The prediction?
Yeah.
The prediction, yeah. Yeah, so we have another script that which is called Valena predict. And once a classification has been so essentially what happens is, what I didn't do here is I should have saved the model into one way, but I have a couple of saved models, so I'm just going to use one of them. I'm not exactly sure, but I don't know, 53 train data, 53 kilohertz. Just choose a random file here. Okay. So essentially what we're going to do here, we have to load a model. I think it was my model, 2 maybe. Maybe like that, something. Then we just have to provide a file, and with the correct path. It says it's extremely confident that it is a 53 kilohertz file. Maybe it is a round off. Must be some round off approximation. So this is how you would then use it for new data, and then you can play the game of supplying a bicycle picture. Which what kind of way that would be.
Thank you, Alex.
That's all. Thank you.
Any other questions, thoughts, opinion?
Just a general question about the micro or the hydrophones that you're using. Do you know what the range of these is, or what kind of sea area coverage?
It depends on the sound source of the sound level of the source and the frequency, because different frequency attenuates at different distances. The attenuation rate with distance is different for different type of frequencies. So that's another thing that would make what you proposing very challenging, is because creating artificial signals is tricky because of the attenuation effects and artifact that you have during sound transmission in the water. So there's some distortion that happens due to this different attenuation of sounds with frequency, and so recreating, for example, a perfect Cuvier big 12 sound, it would be very challenging because the directional sounds, you don't know how far you're recording it from. The problem is that we don't have control of the signal to noise ratio, we're just recording. So what we get, it depends on the relative position of the sound source and the recorder. So we can understand, because we have bibliographic information of what some signals are, but recreating the natural condition under which we should train the system to recognize the reality, it becomes tricky because it's hard to take into effect those attenuations situation in the environment that you have. I don't know if that makes sense. Or was, I don't know if I explained it right, but.
Not sounds convincing to me.
Yeah.
So in terms of orders of magnitude, so how far can a whale be away so that you can still
hear the signal? The fin whales, 20 hertz, they attenuate over tens of kilometers, maybe you can hear 50 kilometers away. But you will never hear nectar dolphins farther than probably, I wouldn't say 1 kilometer is in the best sound transmission situation. It's just because 130 kilohertz of sound, it attenuates so fast in the medium. So that's another challenge. It's like, yeah, when you're looking for something, when you're looking for so many different things, the actual area that you're sampling depends. It's different for different sounds that you actually want.
It looks like it is from the pictures, and they show that you don't have to cope with an enormous noise floor. So it seems that you
have what?
Sorry.
Sorry.
So it didn't look as if you have a lot of noise in these pictures. I don't know if these pictures were particularly chosen to.
What I did is I made a detection program that I wanted to look for this big low sound. So I filtered out low frequency noise, and I was just looking into the right frequency band for that. But for what would be the application of this system, the way that I envision it is like, if we're looking for a short broadband echolocation system, we will do the detection in a certain way, eliminate the noise where the signals are not, and create standardized JPEGs for the classification, and maybe have another system that does the same on tonal calls in the low frequency domain of Wallin waves, because it's like physically that kind of sound is different. So you might need different kind of detection. And yeah. All right. Thank you for. And please give a seminar, Graham. Give a seminar next.